We will now continue to the definition of all of the simulation options. So at first we will define if we want to use mono or bidomain. As you might remember, in the very beginning we set a parser command called source model to have that information passed from the user that enters that information in the command line. And we will now feed that into the the model type options. And the way we do this is by using ep.modelTypeOpts, and we feed it here the source model, which is monodomain or bidomain or pseudo-bidomain. Then we have to give a specific time resolution. Which we can do by using the keyword dt. And here we chose 100 microseconds. Then we can define the input-output parameters, space dt and time dt. And space dt is the time interval in which values are written out from the openCARP simulator to a data file. So you would not write out these values every 100 microseconds. That would give you terabytes of data, but you just sampled them a little bit rougher. So every 0.1 milliseconds, I want a value of the simulator to be written out to file. And time dt is simply the amount, the time interval at which the command line displays updates of simulation. So now what we do is we will create the final command that will be passed to openCARP. And the way we do this, basically it will be a huge string which will then be passed to the simulator. So first we define that cmd, which will be the huge string, will be a carp command with the command tools.carp_cmd. And then we will add all the definitions that we set up in the previous steps. Now, as an optional part, we can add visualization. And we end the run function with calling job.carp. And this concludes our simulation setup. Now we can check the whole thing again and then run it. Okay, so the first thing, of course, we have to add cmd to job.carp, so we pass the actual command. And other than that, we have to also probably add ep, which was not previously defined, and that is added by importing ep from carp-utils. So if we save this, we can now switch and see if we can run our script. So I have now switched to the folder where I created this run.py, and what I will do now is simply run it. And we've set up default values for all of the inputs, so I'll just run it with all the default values we set up. And here, when checking, you can already see that we have two regions and that setting up the two ionic models using different setups. And now it's running the simulation. And once this is finished, we can take a look at the results. So let us now look at the result using Meshalyzer. To open the mesh, we go to the Meshes tab and open block.pts. Two windows will appear. and at first you will see nothing. So in the first step you can compute the surfaces, and here we can already see that we have created, if I rotate this a little bit, we can already see we have created a whole mesh block as a combination of two regions. And we can also see the tags that are given to this region in this little window here. So titled by region, we can see region 10 and region 11. Now, this is simply the mesh. Now we have to overlay it with our simulation results. So we do read IGB data, and we are now in the meshes folder, so we have to go up and go to our job ID, and we can read vm.igb, which is the transmembrane voltage, and overlay that. This creates a black or gray picture. We then adjust, since transmembrane voltages are somewhere from minus 80 millivolts to 10 or 20. We adjust our color scale to that, and then we can simply play our movie, and we can see the propagation running through the fast region very fast, and then once we get to the slow region, the propagation takes much longer to reach the edge. And this simulation, we can watch the whole thing, or we can skip through it with the right mouse button, where you can skip through it a little bit faster. And we can look at the time series. So what we can do is we can show the vertices, highlight the specific elements, pick a vertex, which is now marked with the pink dot, and show the time series on the left hand side. And we can then also pick a second vertex and click on the second region, and we can now see both overlaid here. And the blue one was our first region where the stimulation is in, so this gets activated first, and then the propagation travels across the tissue and activates the cell in the second region. And we can also see that even though the cell in the second region is activated later, it repolarizes faster, because if you remember, we increased the potassium conductance twofold, so this cell repolarizes faster. So even though it's activated later, it's back at roughly minus 80 millivolts earlier than the initial activation in region 1, which is the blue curve. So you can see all our setups worked out, and we have a really nice result. So what have you learned today? Today you've learned of the overview of the workflow, from having an idea to setting up the simulation to visualization. Second thing, you now know the general blocks needed to build an experiment. And also, you know that setting up experiments need not take severely long, but can be done in just a few minutes. And you also know that modifying an existing experiment can be easily done by just simply changing parameters that you have introduced earlier. And also expanding these experiments can be quite easy by just adding known code. For example, to add a new region, you would just copy the block of code and write your own new region. So all of these things you've learned in this tutorial, you can just have fun with that, and we hope to see you next time. Thank you.